Now, as a part of the numerical methods in this course, the first one that we look at is methods to find the roots of an equation. Now, there are two methods that we are going to comprehensively address. One is the Newton-Raphson method, and the second one is regular falsy method. Both of these methods are invariably to be mastered for university examinations. You can notch up around 6 to 7 marks for each. And we are going to demonstrate how these methods can be implemented on a typical calculator that is allowed for universities, and also we would do it on XLS so that you gain complete clarity on what is what. Now, how exactly this method works, we are going to discuss in detail, graphically also, and then develop basic expressions for these methods. But however, the first question arises, why exactly you should spend so much time trying to understand these methods? One of the advantages is these methods can be easily codified. That means you can write your own code so that you can automate your root calculation. And the third question arises, why exactly the root calculation becomes warranted? For example, we have already gone through a detailed discussion of Laplace transforms. There, in order to compute the poles, you will have to solve the characteristic equation, that is the denominator of a transfer function. Let's say if it is a quadratic equation, the solution becomes very obvious because you have done it at the 9th grade. If you are confronting a cubic equation, even that is solvable because we have dealt with several cubic equations, especially when we were finding complementary solution for differential equations. But what happens if you are dealing with a 5th degree equation or a 7th degree equation? You don't have a ready-made formula for these situations. Then these methods, which can be easily codified, become very, very handy for you. And therefore, it is very important to understand the philosophy of these methods. One of the methods, that is Newton-Raphson method, which has a quadratic convergence because that exploits the idea of derivative. And of course, this method can be further improvised and applied in case of the optimization. Here we are going to use it for f of x equal to 0. If you want to use it for f dash of x equal to 0, this Newton-Raphson formula also undergoes a transformation, which will be of interest when you pursue engineering optimization. But here we are just trying to find the root. But the second one, regular falsy method, is far more efficient than other methods, for example, bisection method, but that has linear convergence because that is again based on the idea of secant, but here it is based on the idea of derivative and hence tangent. So first let us unravel the idea of Newton-Raphson method and understand the limitations and how exactly it works in detail, and then we'll move on to regular falsy method, and that is going to be followed by large number of typical university problems which are going to be demonstrated both via XLS for clarity and for implementation in a typical examination hall via calculator also. So let's get started with the discussion. Now let's try and introduce the Newton's method of finding the root. To give a little background, what exactly we mean by roots. Let's take a trivial example. Let's say that I'm talking about the equation x square minus 3x plus 2, that's equal to 0. If I plot this particular curve and if I attempt to find the roots graphically, it becomes very, very easy, because if I plot this curve approximately, then you can easily guess where exactly it crosses the x-axis, because one of the roots that it has is 1, and if I put 1, you can get 0, that is at this particular point, 1 comma 0. This happens to be root 1. Let me say root 1. And if I consider the other point where it crosses the x-axis is 2 comma 0, because if you put x equal to 2, it becomes 4 plus 4, 6, 4 plus 2, 6, minus 6, that is 0. So this becomes my root 2. That is x equal to 2 is my root 2 and x equal to 1 is my root 1. So these are the two roots which can be found easily using a graphical method. But what happens if the power becomes significantly high? Instead of x power 2, if it becomes x power 2, unless you have a graphical tool, it becomes very difficult for you to compute the roots, right? And that is where you can have a quick method called Newton-Raphson method, which can be easily codified. Of course, for academic purposes, what happens, you keep on iterating, which is painstaking. But if you want to implement this particular method in a practical situation, you would obviously write a code, because you can readily develop a formula for this particular method, and which can give you answers very, very quickly. Now, let's try and understand how exactly this method works. Here goes the diagram. This is the typical function that is in red, which is plotted. Okay, let's say this is your f of x, that's equal to y, right? Y is equal to f of x is the function. It can be a parabola or anything. Let's say y is equal to some ax square plus bx plus c. Wherever y becomes 0, that means the roots of this particular equation can be found here. That is, there are two roots. One is this, it is crossing the x-axis, and another root which is over here, there also it is crossing the x-axis. These are the two roots which we'll have to start. Now I am trying to find this particular root, and I am incepting at this particular point, as my initial guess. Why my initial guess is on my x-axis? Because my root is also the value of x, which makes this function go to 0. The value of x which makes this function go to 0, if I substitute the value of the root here instead of x here, the f of x actually goes to 0. So that is my root, that is the value of the x coordinate, and therefore I incept with my guess on the x-axis. Okay, you can see that that is my initial guess. Once I make the initial guess, what I do, I draw the vertical to the parabola, or the function that is in question, and then wherever it actually cuts the parabola, there I draw a tangent. That means you can see that I have drawn this purple color tangent. You can see at that particular point where my initial guess in fact intersects the parabola, the function. There I am linearizing that parabola, that function, by this purple tangent. How do you linearize? Because by now you know the concept of linearizing. A curve at that point instantaneously it is linearized by a tangent. The value is mimicked by a tangent, just like surface is linearized at that particular point by a plane. So tangent plane, but here it is just a tangent. And wherever that tangent cuts the x-axis, that becomes my first iteration output. That means after first iteration I get my root as 3.5, but that is far away from the actual root. So the error that you get when you substitute this particular value of x into this equation is significant, and therefore I continue to iterate. What I would do, I would draw one more vertical from this 3.5 to the parabola. Wherever it cuts, there I draw one more tangent. You can see the sky blue tangent which we have drawn, and that when cuts the x-axis, we will get the second value of iteration, second x that is out of the second iteration, and that is very, very close to your root. If that is substituted in this particular equation, then you will get almost y equal to 0. And that is why if you numerically evaluate this method, you would find that it is converging quadratically. That means if you have an error of 0.1 in one of the iterations, the next iteration would reduce that error to square times, that is, it becomes 0.01, right? We would in fact demonstrate that as we go through the numericals. Now let's try and develop an expression for this particular process. Let's say that you are starting with an initial guess. Let us say your x naught. Let us say this is your initial guess. All right, this is your initial guess. Now what happens, you from the initial guess you draw a vertical to the curve or the function whose roots you're trying to find, and at that particular point where this vertical intersects the curve, you draw a tangent. You can see that the purple tangent is drawn, and then you get your first iteration value. So what exactly you got to do, you first find the expression for this purple line, that is the tangent, and wherever it cuts the x-axis, that gives you the value of first iteration, right? You start with your initial guess, and my aim is to find x1, which is your first iteration. So how do you find the value of the tangent? The value of tangent is very, very easy to find, because you know the slope of the curve at x1, y1, slope of the curve you know, and then you also know what you want to find. You want to find the point where y becomes 0. So therefore it is very, very simple. I'm going to use the 2-point formula for the straight line, that is defined as y minus y1, because you are drawing the tangent which is passing through the point P with coordinates x1, y1. So the 2-point formula is y minus y1, which is equal to the slope. Now the slope can be represented as dy by dx evaluated at what? x1 comma y1. Of course you require only x1 because your function is y is equal to f of x. So therefore you can as well write this as evaluated at x1, right? Because y is an exclusive explicit function of x, and therefore if you just differentiate you will get one more function of x, and if you substitute x1 you'll be able to find the value of dy by dx. Y minus y1 is equal to slope into, which is dy by dx, into x minus x1, right? So this is the equation of the tangent. Now here, when this tangent intersects the x-axis, that means when you say y is equal to 0, you want to find x, which is your first approximation. First approximation, right? So this is the value you want to find when y becomes 0, because this is the equation of the tangent. What did I do? I used the 2-point formula. I know that when my first guess is taken, I draw a vertical so that it intersects the function at x1 comma y1, and I can evaluate the slope of the curve at that point, because at that point tangent approximates the curve. So it is dy by dx evaluated at x1, and then x minus x1, y minus y1, because this straight line passes through this particular point. And once I get this equation, if I put y is equal to 0, where it happens at x equal to the value of first approximation, right? So therefore can I take this to the next slide? So now it is very, very clear, that is y minus y1 is equal to dy by dx evaluated at x1, that is my first initial guess. So x1 can also be written as x0, because I said my initial guess be x0. So you can also say that x1 is equal to x0. Clear? x1 is equal to x0, that is my initial guess. Now I am trying to find my the first approximation. So can I replace here also x by x0, my initial guess, and of course y0 also I can replace here, because when I say this is x0, the corresponding y coordinate is also y0, my initial guess. So now what happens, I can replace this by another set of symbolisms. Can I say this as f of x0? Because my value of the function at the initial guess, value of the function at initial guess, remember, because y is always equal to f of x. Y is always equal to f of x. And if I say my initial guess is y0, then that obviously must be equal to x0, f of x0. Y is assumed to be an explicit function of x, right? So that is equal to, now can I write this as f dash of x naught, f dash of x naught. And now this is my first iteration value. So let me say that it is xi, first iteration, and minus x naught. In order to get my xi, I must make my y 0, because this is the point where the curve crosses x-axis and I get my x value. So as a consequence, what happens? I get minus f x naught divided by x dash of x naught, and that is equal to the first iteration value minus x naught, right? If I simplify that, what I will get x naught minus f of x naught by f dash of x naught. That becomes my first iteration value, and therefore if I square bracket it, so this becomes my formula for this. So x naught, the first initial guess, minus f of x naught by f dash of x naught, that will give me the first value, first iteration value, and this continues. Now what happens for the next iteration? What you would do? You would simply replace x naught by xi. For the next iteration, you will replace x naught by xi, because go back to the figure and see what happens. First I started with this guess x naught. Then once I calculated the first iterative value, that becomes my initial guess for the second iteration. Remember? So therefore, if I write this systematically, if this formula, if I take it further and write it systematically, my first iteration is initial guess minus f of x naught divided by f dash of x naught. This is for the first iteration. If I seek my second iteration value, what happens to x naught? X naught is simply replaced by xi, because once again let me tell you how exactly this process proceeds. You started from here, you dropped vertical, and then wherever it intersected the curve, you drew a tangent, and then this became your first iterative value. You dropped a vertical, and then you drew one more tangent wherever it intersected x-axis. That becomes your second approximation. So the process is essentially very, very simple, but very powerful, because it is quadratically converging, because thanks to using f dash. So f of xi, because this becomes your initial guess. So x naught you started with, you computed xi, the first iterative value, so that becomes your initial guess for the next process. So this continues, because this becomes fi. If I write my third iterative value, so that simply becomes f x double by f dash of xi. So this is very, very easy. So this becomes your initial guess for the process to incept. This is your first iterative value. So that is used as initial guess for the next process. The next step process, whatever output you get here, that is used for the next process. So this is first step. This is step 2. This is step 3, and this continues until you get a good convergence. How do you actually get the convergence checked? You would see that your value of x3 and x4 do not have significant improvements. Suppose you, let us say that you get, let us say here you get 4.1. Here, let us say you get 4.05. Let us say here you get 3.95. You are moving towards the root. And in the next iteration, you will get 4.94. Next iteration, you will get 4.398. I think here the improvement between these two roots is significantly small. This is where you can halt the number of iterations. In fact, in coding, you can specify that this is the percentage of increment between the preceding and the succeeding value, then you can halt the number of iterations. You see here 4.1 to 4.05 significant, 3.95 also significant, but 3.94 it is almost 3.94 the next iteration. So if you find the next iteration, it can be almost 3.9389. So you can halt the iteration. This becomes approximately your root. So this is very, very important, and also for those who are highly motivated can in fact research that a Newton-Raphson formula looks very much like this, but only thing is here you are trying to do this f of x equal to 0, you are trying to find the root. There you are optimizing, you get f dash x of 0. So therefore this becomes f double dash and this becomes f dash. It is almost like integrating these two factors to get to those two factors. So therefore this is very important. And of course the Newton's law comes with a lot of limitations. Suppose if your initial guess is not at all correct, you are headed nowhere. It has to be scientific and it should be thought through. So that is why initial guess is very, very important, which can make your process very, very efficient. And second thing, what happens if the roots are repeated? So all these questions are going to be answered as we walk through several numericals. But the process is very, very simple. This is the process. The initial first iteration value is given by initial guess minus the function evaluated at the initial guess divided by the derivative of the function evaluated at initial guess. Ensure that this does not go to 0. Otherwise, it makes no sense, because it becomes ill-defined if it goes to 0, because this entire term tends to infinity. You have to be careful on that. So once you get the first iterative value, that becomes the basis for your second guess. So it's very important for you to understand how exactly this process incepts. You incept with the initial guess, cut your function, draw a tangent. When the tangent crosses your x-axis, you get your first root, then drop a vertical, then draw a tangent. This continues till you hit the root very, very closely. So this is very, very important. So your convergence is determined by initial guess. If you were to make a guess far away, then it would have taken large number of iterations to hit at the root. So let's consider the numericals, which will give you much more clarity. But nonetheless, the formula that you got to remember that is very, very important is this. This is derived based on basic 2-point straight line formula, because if you looked at how we derived it, it is slope into x minus x naught. That is the point at the initial guess is x naught comma y naught. Okay, so if you substitute that in a 2-point formula, that is y minus y naught into slope into x minus x naught, you would be able to get the value of x when y goes to 0, because that is when this straight line crosses the x-axis. When this straight line crosses the x-axis, your x becomes the first iterative value and your y becomes 0 at that point. So we put y equal to 0 and get this expression, and when you simplify, your initial guess minus this ratio would give you your first iterative value. But ensure that you don't have a situation where f dash of x naught goes to 0. It should be finite one, because after all you are dividing. For this to be mathematically valid, you should make sure that it does not go to 0. So let's move on and look at numericals on Newton-Raphson method. Well, engineering and math are absolutely inseparable. We interventions day in and day out try our level best to make math as simple as possible and also of great practical value to every aspiring engineer. Do you want us to reach the masses? Please like us, share and subscribe. Do not forget to turn on the bell icon.